Professor Ganapati Rao Myneni. He's from USA, Virginia in particular, and the topic is thorium converter, ThorCon, a doable molten salt reactor. Professor Ganapati is unusual. He has two chairs in Virginia. One is he's Taksha Professor of Physics and also is Professor of Homeopathy. So it's an unusual combination. He graduated from IIT Madras, Chennai now, and his PhD work was carried out at Fritz Haber Institute of Max Planck Society in Berlin. And then he doctoral work was conducted at the Institute of Cryogenics in Southampton in England. And his areas of expertise and experience include low temperature physics, vacuum and cryogenic instrumentation, surface science, hydrogen and matter, and superconducting science and technology of ingot niobium. So I don't know how he came into thorium, but he's doing thorium converter.
Well, I can answer that question to start with. I'm a low temperature physicist. Huh? The reason I became a low temperature physicist is because of monazite sand, which was basically taken away by Dutch way back, I think about 100 years ago or so. They smuggled it because they had one of the scientists' brother is working here as a diplomat. So they heated the monazite, they got the helium.
Okay.
So that developed the whole field of low temperature physics.
Okay, I want to add a little bit. Professor Myneni got an appointment from the governor of Virginia, and he presently represents several scientific organizations in universities in Virginia, and he serves on the Virginia Energy Council as a representative of Virginia Nuclear Energy Consortium Authority. There's all kinds of organizations he represents. Okay.
Okay, I need to finish answering your first question anyway.
Okay.
How I got into this. I came to India after 10-year break in 2006 to attend a conference in Bangalore, International Linear Collider.
Okay.
So at that time, I was working on this ingot niobium technology. You heard that India is interested in ADS. If you can do that, you can avoid all these fast breeder gimmicks. So in that connection, I was invited back to come and talk to them about that technology because they would like to use that technology. So that led to interactions with Dr. Srikumar Banerjee.
Okay.
So while I was sitting in his office, I think in 2007 or 8, I don't remember exactly. So we said, all right, Fermilab, which is interested in interacting with India so that they want to get some help to build their future programs. So that will be pulsed power systems, pulsed Linux. So we said BRC requires for the ADS systems CW Linux, superconducting Linux. So since Jefferson Lab is basically expertise in that area, we said we will focus in that.
Okay.
So that led to the formation of the Virginia Consortium on ADS, and also, which is a part of Jefferson Lab and other activities. And also I have a nonprofit which is trying to understand the effect of hydrogen, particularly in niobium, how it influences the superconducting properties. So this is the whole connection with, that's how I got involved into this.
I guess you're associated with energy, and this is an energy producing system.
Yes.
Yes, okay.
All right, so I'm going to be talking about this ThorCon doable molten salt reactors. I'm sure some of you must be having doubts. What is this business of doable? Is it a legal word? Any of you have objections for me using doable molten salt reactors? Then I'm in good company. Because my boss told me, you know, he's an English guy. What is this doable? There is no such word. I said, we want to make that happen so that can be doable. Well, anyway, So ThorCon reactors are supposedly, or we hope to, produce low-cost, dependable carbon dioxide-free power. This is the schematic or whatever artistic impression of that. And what is the energy situation? We heard last few days what is going on, but this is the overall view of it. In the world, what the power consumption expected as a function of years, you can see is about current one, the lower one is for the fissile fuels, and if you extrapolate what is expected out of those systems, you can see there. And then the total world power is basically, including everything else, is on the top graph, and that's what is expected to be the demand. This is based on assuming that each person consumes about 1 kilowatt, which is happening in Europe. But I think I heard another figure, 2 kilowatt per person. But anyway, so expected population growth, future would be about 10 billion. And if you take that into account, you need about 10,000 gigawatt equivalent electric power. And also we need for transport, industrial heat, synfuels. Transport, basically you could also use hydrogen, right? So if you have high power, high temperature reactors, you can produce hydrogen, you can develop a hydrogen economy. That's another aspect we could think of. But anyway, so the demand could rise to 70,000 gigawatts. So only nuclear energy can do this job with low environmental impact. I think that's what we have to keep in mind. So to successfully compete against coal, to produce this kind of power, you need to have volume production. So that means one should be adding 101 gigawatt units per year. So these are like, aircraft numbers. Airbus or Boeing, they produce wide body airplanes more than 100 per year. So that's all you have to do with nuclear systems to meet that requirement. So our chief ThorCon expert in this is Jack Devaney, who was a professor at MIT in, I think this is on ships and so on. Basically, he built world's largest crude carrier, which is shown here, at a cost of $89 million. That was in 2001. I don't know whether you can see these figures here, but the bottom line is the following. This is only about 1/3. The 1 gigawatt nuclear island we are talking about is only 1/3 of the ship. So the cost, the resources you need for building that island is very small compared to what ship requires. And the main thing that you need to look at is what is the, molten salt needs to be moved around. That has to be done at 14,000 meter cube per hour, whereas the oil discharge in these things are 15,000 meter cube. So this is a comparable number. And the largest component in this ULCC is the diesel power generator, which is about 35 megawatt. Whereas in the case of nuclear island, you need about 500 a crane which can lift 500 tons of these loads. I think that's all you can say. So ThorCon uses only 1/4 the steel, and it's a very simple construction. I think that's what I think we should take from this. So ThorCon would like to use this shipyard technology mainly because the productivity is high. That's what this view graph shows. You can see the numbers. And you can get 4 to 5 man-hours per ton of full hull steel. That kind of productivity you can achieve in producing these nuclear plants. Shipyard quality is very important. They, as you know, they have 150 to 500 ton blocks, and they are produced with very precise dimensional controls, and they are inspected really on the assembly systems. If there are defects are found, you can really correct them right there without affecting the schedule. The best comparison is if the ship has to be off for 15 days, basically it is 11. So that is a comparison in these technologies. So building on everything on an assembly line, that is the core principle behind this ThorCon technology. You take a shipyard, which is here an example. It's a Hyundai shipyard in South Korea. This can actually produce something like 10 1 gigawatt plants per year. So this is a line, basically it's a production line. You have primary loop line, can hold up, tank line, membrane wall line. So you can see the major components are produced in lines to get these kind of efficiencies. So what you do, you basically build a largest of these blocks in a factory. So mainly the block size is limited by the transport system. 80% of world population lives within 500 miles of coast or major river. So targets using these badges allow much larger blocks than train or truck. That's what the concept behind. And so this badge has to be about 23 meters wide, and height depends on the river or open. These are the limitations. So the main thing that limits is the 500 tons for each of these components. So as you see, this is the shipyard, and here is the barge that will transport the main components to the site, and this is the nuclear island. And then you have to have another shipping, this is called can ship delivering system. Basically, it takes the used cans from here after 4 years, and it pulls another 4 years, and you basically make one trip to the island to take the old ships and bring the new one in. So it's all done in one trip. So what it requires, you can potentially have business in the area of can recycling center, and then also a fuel recycling center. So besides of the reactor business, you also have possibilities to build side-by businesses. To successfully compete against coal, we need to have a very safe system. No way to threaten cities, or we only can use fewer skilled operators. So this is the outside view of the ThorCon design. As you can notice, the nuclear reactor systems are actually underground. I think this is the very important aspect of this technology. And the barge comes in and basically loads the cans into this system. So let us dig into how it looks like. This is the overall view of the island. You can see it's about, I can't even read myself here, around 300 meters here, I think. Maybe another 300, 200. Yeah. So this is overall, and here are the, this is a 500 megawatt electric. This is another 500. So total will be 1 gigawatt, and you have 2 turbine halls, you have a switchyard, and this is the cooling towers. And what are the internal systems of this reactor? There's a can, which is a nuclear module, which is about 250 megawatt equivalent. So this is all going to be underground, as I said. Of 2 cans, they are actually duplexed to accommodate 4-year modulator life. So basically, you can operate for 4 years, then cool down for 4 years, and then you change out the can. That's the concept. So here you are seeing the 500 megawatt typical power plant. It has 2 250 units, and basically the turbine will be a 600 megawatt turbine for this system. The specifications for the turbine system are same as the coal plant. It's most cost effective. So the ThorCon's heart is the can, which is shown here, and this is the pot, which contains the graphite to slow the neutrons down and heating the fuel salt to somewhere up to 564 to 704 degrees C. Converted portion of thorium to uranium-233 and uranium-238 to plutonium-239. That all happens in the pot. Primary heat exchangers transfers heat to secondary heat exchangers. Here you have the main big component is this pump moving this salt around and exchanging the heat in this primary heat exchanger. This is a major moving part in the whole yard. So the pot pressure is about 4 bar gauge. Pump header tank extracts the fission product gases. So there is a fuse valve here. If there is any overheating of this system, it automatically opens this plug valve and drains the fuel salt. This is similar to other things you have already seen. So this is the fuel salt drain tank, and no operator intervention is required, as you heard from other concepts. In most cases, damage is limited to the can changeout. So the has also the same principle used in the AHWRs, passive cooling. And this is the membrane valve, which basically changes heat from these systems by radiative as a T to the power 4, so it can rapidly heat up. No passive cooling penetration into the can or into this fuel drain tank. There are 2 barriers between the fuel salt, which is in the tank, and the membrane valve. So membrane valve basically removes the decay heat. So when it rises, it goes into the cooling system, and then the green one is basically water coming back. This is a natural circulating loop. So basically, this system can survive without any intervention up to 100 days. The ThorCon is actually a 4-barrier design. What you are seeing here is the can. That's the first barrier. And then second barrier is the drain tank, which is 5 bar ore pressure. Third barrier is the silo cavity, inverted. It's duplex and duplex barrier there. And the silo hull is the next barrier, which is designed to be about 1 bar ore pressure. This is the next. So basically, there is a 5th barrier here that could be the fuel salt chemistry itself, could be the 5th barrier. So here is the ThorCon neutronics, both MCNP and serpent models tied to the ThorCon DNA, both for the pre-processing and post-processing was involved. The core is made up of 380 by 22 by 4 centimeter slabs arranged into hex locks in 5-meter cylinders. Easy to fabricate, easy to disassemble, lots of surface area for heat transfer. So 84 moderate locks. Central locks are replaced with 1 regulator and 3 shutdown rods, and also for instrumentation. So burn-up based calculations are based on serpent and clever fuel adjustment algorithm by Manu, I can't say his name right, he's at Grenoble. So the current work aimed at extending this work, including explicitly modeling decay outside the pot. So ThorCon is basically both fuel and salt flexible. So the initial tests will be using NABE, salt, and the fuel would be uranium, 100% of it, but that's which contains 3% of uranium-235 and 97% of uranium-238, and the makeup would be basically the same. So this can generate up to 30% of fuel, but the economic way of operating these ThorCon systems are again the same fuel salt, 82% of thorium, uranium is 18%, but this is enriched. It's going to be 20% of uranium-235 and 80% of 238. Makeup is also this. And self-generated fuel in this case is 50%. And if you have flyby available, basically you can get better fuel utilization, and basically everything else remaining same except the self-generated fuel goes up to 60%. The best fuel utilization is 4, case number 4, where basically you are using 82% of thorium, uranium 18%, which is consisting of 12% of uranium-233 and 88% of uranium-238, and the makeup is 12% uranium-233 and 88% of uranium-238. This is almost 100%. You could also run this system in a breeder mode. In this case, you need to load 97% of thorium and 3% of uranium, which is basically 61% of uranium-233, 8% of uranium-235, and 31% of uranium-238. This actually generates fuel for you. So the 4, what is happening here is you need to do on-site vacuum distillation at 1.6 liters per hour to separate seeker fission products such as plutonium, americium, and then it sends the plutonium to a fast breeder reactor, and it can receive back uranium-233 from the fast breeder. So in principle, you can include fast breeder systems into this loop. So number 5 case is basically same as 4, but it allows the use of highly enriched uranium in reactor, and it can also ship back the fuel. Makeup is all thorium in this case. To successfully compete against the coal, we need lower cost electricity. So how do we get there? So if you look at the system here, these are the reactors underground. This is the turbine halls. So what is the should cost versus did cost? Should cost is basically based on how much of the plant's precious resources we consume. That is steel, concrete, nickel, productive labor, etc. Based on resource usage, ThorCon should have a smaller capital cost than coal if you want to compete with it. And ThorCon volupes coal on fuel cost. So you'll see in the next view graph. But there is no limit how costly regulation can make any technology. So this is addressed the other day. I think that is the main question, and that I think we need to understand. So unless we narrow the gap between should cost and did cost drastically, no nuclear technology will be able to compete with coal. So to compare with coal plants, here is the turbine hall, because we are using the same generators. And you require all this infrastructure in case of coal plants. So that's why this will be cheaper than coal plants. So which can be seen here. Steel and concrete required for the steam generation of a 1 gigawatt plant. And steel in metric tons for ThorCon is 18,000, for coal plant 91,000. The ratio, it's 1/5 of coal plant. Concrete is 1/3. So ThorCon requires an extra 100 million of a nuclear specialty items for a gigawatt plant. That would be graphite, stainless steel 316, ANS 230, lead, and excavation. So estimated overnight cost of a coal plant is $1,000 to $2,000 per kilowatt, which is about 60,000 to 120,000 rupees per kilowatt in Indian currency. Estimated overnight cost of ThorCon is about $1,000 per kilowatt. So what is the levelized cost here, coal versus ThorCon? So here is the coal. The capital of the plant is 0.0154. Fuel is this much here, and operations and maintenance is this. Total cost for coal per kilowatt hour is 0.0 $0.437, which in rupees is 2.62. In case of ThorCon, the capital investment, though it should be smaller, but we are taking a conservative value of the same. The cans cost an additional cost of 0.034. The fuel is much less expensive than coal. And salt costs need to be added, and the operating and maintenance are smaller. So the total of per kilowatt hour is $0.02, which is equivalent to 1.74 for ThorCon. So you can see very clearly that it competes in the cost per electricity produced in comparison to that. So the other important aspect of the ThorCon design is fixability. So don't pretend that things will last for 30 to 40 years. That is never the case. So one doesn't know what is the mean time between the failures. So even if we did, things are going to break down. Murphy's law, right? So everything but the building must be replaceable with modest impact on plant output. This is the crux of this design, the philosophy of this plant. So the existing nuclear challenge, when something breaks, it can be very hard to go in and fix it. Whereas in the case of ThorCon, this key problem is with duplexing. We have two cans. The second can is sitting there in the silo. Basically, you switch it over. It can be done within 24 hours. So what is it? This has to be done now. If you are going to make any successful impact in the human health in the world, we heard that in China in 2013, 400,000 people died because of air pollution. If you want to prevent that kind of stuff, we need to do it now. So what is the market? We have about 1,400 gigawatt electric of new. These are the things that are being built. So we can replace coal plants with ThorCons very effectively because we can build them now. What is ThorCon is about? It is already, you heard about molten salt reactor experiment at Oak Ridge. Actually, the anniversary of that was October 6th, and they are actually running a workshop tomorrow and day after as a centenary, 50 years of celebration. So what is special about it? We are not trying to invent any new technology. We cannot wait for the flight. Forget about breeder to compete with coal right now. Forget about fancy fuel processing, waste burning, and all those things. Forget about Brighton. Use the standard steam cycle, which is available very cheap. So all that was done here is scaled up from this 8 megawatt to 250 megawatt electric. That's all done by the ThorCon group. We can put the prototype out to bid in 6 months. We can start pre-fission testing on a full scale and prototype in 24 months from now. If all goes well, we will be in a position to start zero power testing in 48 months from the start. So this can be done in that time frame, and these are the examples. So this was built in 2 years, way back in 1959, a 2 megawatt electric system, Camp Century. This is a Natalius submarine, 10 megawatt unit, pressurized water, electric boat. This was done in 4-year development and 2-year construction. Hanford, 250 megawatt thermal plutonium production system by DuPont, and GE was built in 2 years. So these are the examples way back in early 19th century. So the ThorCon design philosophy conquers the enemy, the time. Now, no new technology. So we do not need to do any new research, no unobtainable materials, shipyard production and speed, replaceable irradiated materials, steam power conversion, factory quality control, fixable replaceable parts, no scale-up decay. So this is the time scale that can be done. Seed, year 1 is the seed. Phase 1 takes place in the year 2. Phase 2 up to year 6, and then construction of the yard for the plants. You can start deploying ThorCon units at year 7. So as I mentioned, ThorCon prototyping can be done within a year. And this is the time scale of the program. So all that needs to be done is a 3D model and then seismic calculations, prototype specs, negotiate contracts, and these are the tests that needs to be done, NABE tests and the twisted tube test, primary loop pump testing, and the build prototype, pre-fission test, order turbine generator, expand first cryo module, ramp up to full power, order build second cryo module, and full power test starts in about 5 years' time. So the cost, what are the costs involved in doing this? The seed funding for the first phase is $10 million, and second phase is going to cost $75 million, and the third phase, $400 million. We must have an efficient regulatory environment for this to happen. So this is the main crux of the problem. So as you know, there is no limit on how costly regulation can make any technology. So if we use the commercial aircraft model, you build and test. You build and test, not the computer paperwork that is done at NRC or any other places. So I think that's what we need to look at. So the plant must be modular to make such testing feasible, but we need big modular, not small. So basically, the first prototype would be full-scale version. So to do this, ThorCon needs a country. The country that wants cheap, reliable, carbon-free power, which wants a Boeing-style export industry, is willing to host waste and fuel recycling facilities, is willing to regulate efficiently. So ThorCon, a team is asking India, do you want to be that country? So here we go.
Thank you very much for this provocative paper, and we can ask some provocative questions too, if you like to. Okay, there's some woman there.
Sir, actually, the last slide has excited me. I'm an ex-army officer, and my name when I was in the government was Vyakul Bharat.
Pardon?
So I said the last slide has excited me. That's why I got up, sir.
Oh, okay.
Yeah, because my name is Vyakul Bharat.
Oh, okay, wonderful.
So Vyakul means anxious India.
Yeah.
Okay, and it's a fact. So in all the anxiety, now I cool it down because I'm a retired army officer now. So may I ask you two very primary concern of mine. You have to address it at length because you are a learned person. Wonderful presentation. Proliferation and safety.
Safety, I think we have detailed presentation of how the system is safe. It's walk-away safe.
You mean to say all the tech docs of defense in depth and everything from IAI, we should forget, and India should work on its own? Or do we look at tech docs?
Look at cost?
Tech docs from IAI.
Oh yeah, okay.
I'm just asking you, sir. I mean, please don't misunderstand.
No,
it's a concern. Sure. I told you, it's an anxiety. You address it.
Yeah,
so it's not about your safety. I'm talking about international norms and standards. We have the best person chairing this session. I would want him to throw light on that tech doc thing in the coming time now. But you answered my concern of safety regulations, international, global, as well as India, because you are asking us this question. Second concern is proliferation. It's two things I've asked.
Sure, sure. Well, that issue exists with the existing reactors as well, right? So the main advantage of this is you can build it now. They are walk-away safe. And other things you're already doing. So I don't think that is a big question mark. These are the designs are walkaway safe, very clear. The other stuff we can discuss. Yeah, that's what I thought. Yeah, we should discuss that, yes.
Okay, the question there first, yeah.
Yeah, hello. I'm M.K. Sapra from BARC. I had two questions. One is that you said this ThorCon are, of course, our ultimately kind of a small reactor which you are trying to perceive. We are comparing this industry from automobile industry. You said Hyundai has a plant like wherein we can leak for 100 units.
Shipyard.
Yeah, shipyard, yeah, of course. Yeah. So probably we have to think of nuclear industry down the line, or it could be a parallel production line, wherein you perceive, I mean, you are free to, sure, you can really think, and one has to have a perception of tomorrow's imagination could be a reality of today's.
Actually,
one is, no, let me complete it, and then probably you can throw some light on that. That one is automobile sector. Yes, of course, we are looking for the products which should be have a reliability and, of course, good amount of safety, but large number of pieces. Then you said Boeing, which no doubt has a marginally much higher safety than automobile industry, yeah, and has a millions of components. And then they're able to come out with a product which is really remarkable. Now look at that, and my question was a bit concerned with the earlier question. Now this nuclear industry, you feel kind of a timeline, and then we should have a product baseline, and we should be able to produce small reactors, or I would say let us say SMRs, small modular reactors, over the line, and then again how to bring those safety, regulatory aspects, the cost, and of course, end of the day, fuel cycle. When everything you feel it should be in so compact and so emphasized, then multiple governments and safety and security of the whole nation. No, I mean, looking into all these angles, where you place and how do you perceive this product and maybe a ThorCon itself?
Yeah, I think basically we need to understand what are the issues, what we need to do, are we on the right track? And everything else will fall in line once you understand the limitations of what we are facing. With respect to the governmental, I don't think that would be a problem. It may take 1 or 2 years to get the licensing, all that. But if India wants to host this, this could principally become Indian technology. ThorCon is willing to offer this. And we know for sure on the near Visakhapatnam, there are new shipyards are going to be licensed. And I know a group which is interested in actually building the yard for producing these things. I don't know whether I'm answering your question completely, but all those can be addressed. I think if we look at the bigger problem that we're all facing, all these are nothing. The issues you are raising is nothing compared to the bigger issue of the air pollution and the poverty that we need to address, particularly in India. I come from here, right? I grew up with no electricity. I see the pain, but there are a lot of people out there. Health and prosperity is tied to energy. You understand that? So this is the bigger picture. There's a lot of humanity out which we need to bring them up. But all the other issues can be resolved. It's not a big deal. If you have the right mind, I think it can be addressed.
What is the ground reality? Where does ThorCon at the moment is? I mean, product design and analysis spaces?
Pardon?
What is the ground reality? I mean, where is the ThorCon product like starting from design
analysis? Actually, there
analysis?
is a website, the ThorCon Power, you can go. Every document is there. Okay. It's totally open.
Excuse me.
You can go and see it, except the calculations and that kind of stuff are not there.
We'll look into it. Thank you.
But everything else about the system is open to anyone to go and see.
Thank you.
We can have this discussion outside. I think we have time issue here. Okay, there's more questions here.
I have a small question. Is your ThorCon licensed in the US?
No, it is not. We do not plan to go to US for licensing. It will require billions of dollars and at least 25 years. You don't have 25 years. You will be killing a lot of humanity in the meantime.
I just wanted to ask if that last question, is one that's open to all countries on the planet.
Yes, sure.
Not just to India.
It
Because
is
I
open
think,
to anyone. Anyone can.
right,
Yes.
we need to be thinking globally.
The
This is
reason
a
why
global
we, yeah,
issue.
it is a global. It's a
Great.
global picture. But the reason why we are saying India is India has the
Well, we're here right now.
1.3 billion people.
Right.
This is where we can make the biggest impact. And India has the facilities. India has the manpower. India needs it.
That's fantastic.
So this
But-
is a match. It's a real match. I think India has to wake up. Actually, yeah, I have another talk this, I think in a little bit. I will go a little bit more into some of these perspectives.
Okay. The reason I asked the question is because what we're speaking about, this whole convention, is about a global issue.
Yeah.
So the idea of thinking nationally is 20th century thinking.
So the thing is,
So 21st century thinking is thinking globally. You know,
let
so
me
I
say,
just hope we're all on the same page.
on behalf
that's
of the ThorCon team, I can tell you, these are the people, they do not need money. These are the people almost at their prime time. They want to contribute something to the world. They do not need to make profits out of it. There is no motivation here to make profits. They want to see this technology utilized for the global health and well-being. That's all behind it. That is Jack Devaney's wish. He's 75 years old, and he would like to build it. It can be built in 2 years' time. And actually, the first unit is going to be built on a ship, and then take the ship, put a hole, and dig it, go and put it in there and test it. So we would like to do everything on test base, not sitting on papers. What happens in NRC? You asked NRC goals. US is not hungry. They don't care. They should care. That's what I'm going to talk about. In 1953, August 8, President Eisenhower said, atoms for peace. And India was at that time in the prime. You know, you built the first reactor in 1969. I was surprised to see what happened between 1969 to 2006. Nothing was built. I don't understand. But anyway, there's a lot we can learn from the past.
We're going to change that.
Thank you. I think there is someone from IAEA here. Are you?
Who's from IAEA?
I think we need to work together. No,
is there somebody?
IAEA is supposed to be the depot for this kind of stuff.
Can we ask that question there in the back there? I think this paper needs a lot of discussion, and we can't have the time that much, so we better. Okay, ask short question, please.
No, I don't have a question. I just want to get the opportunity to stand up and address the statement that the IAEA has the responsibility to promote this. We have the responsibility to promote the peaceful use of nuclear energy. That's one of our
what we're
visions.
talking here.
However, we're promoting that from a needs perspective, from the member states, of which India is one, of course, one of the major ones. We're not promoting it from a vendor's perspective. So I will be giving a presentation later on, kind of at the same level. I'm not going to get into much details, but if there is an increased interest in a certain technology, whether it's molten salt or thorium as a fuel, and this is shared by many member states, and of course the IAEA would be willing to bring together the experts and select or evaluate under current, of course, IAEA standards and regulators, bring in regulators as well, which is very important at this stage, to make it happen.
Yeah.
So can I have one small question or a suggestion? One step that may be useful for you and other vendors to do before offering it as
excuse me, I am not a vendor. I am a scientist. I saw this one. I learned about it last May at a meeting. And actually, they came and presented at my workshop. I did
rephrase this.
Yeah.
And any product should be reviewed by a regulatory authority.
Absolutely.
Because that is, as you identified it, one of the biggest potential costs. But there biggest concern is safety. So having it reviewed, not necessarily by the NRC, but one of the competent or consortium of competent regulators would be a good idea for any new concept.
We would request IAEA. The thing is, time is the essence. If we can do that under the time frame we are talking about, please.
We'll talk offline.
Yeah.
Okay. Okay, that gentleman, yeah, you please ask the question.
Sorry.
But
see, normally when a country tries to start something new, like our Kodanglam reactor, we also talk of fuel assurance for the entire lifetime. Now you talk of fuel of different kind. I don't know what is the scope of or duration for which you think this, if at all somebody enters into a contract with this, what duration you will maintain the contract and how long it will take place? There is no assurance as to how long, if at all, if some country starts business with you, how long you think you can
I think the ThorCon team would sign the contract to promise the fuel.
Because you seem to have abundant resource of all the material which we are trying to collect.
No, I mean, if the concerned parties agrees that this is the right thing to do, I think all these are all minor issues. They can be resolved.
I think